All right, so this is a similar quiz review to the last one. This time it's slightly different. It says a plate of nachos loaded with toppings is at rest on a dining room table. So let's go ahead and draw that. I don't know, maybe something like this. All right, plate of nachos. There's the plate slash bowl. Okay, and it says the same smart dog is able to lift the end of the table with his paw at an angle of 20 degrees. All right, so this is 20 degrees down here, and this, let's see if I can draw a dog. Oh geez, I didn't do that. I don't know what happened there. Let me see. It's not as good as it was last time. Okay. All right, so about the same, I guess. All right, so this dog is able to lift this table up, and some dogs are really smart like this. I don't know what to say. You can't leave anything around them when it comes to food if it's near the edge of the table. It's like, or if you're eating and your plate is like, and you're not using the table and you're just kind of setting your plate on your lap, like they will come up and take something off your plate. And these dogs are that smart, right? They're the ones that like make you pet them. Like if you're like just sitting there, they'll like nudge your hand to like, to pet them. I don't know. Some of these dogs are just really smart. I don't know what else to say. 20 degrees where the plate begins to slide. If the mass of the nachos is 1,500 grams. Okay, so let's do a free body diagram. But before we do that, we should do something with that mass. We should write it down somewhere. Let's go ahead and, I guess they kind of tell us, no, they don't. Okay, so I'm just going to write it down because I know that this is the mass. So 1,500 grams is equal to M. Okay. I'll use a little highlighter there just to make it stand out. All right, I don't want to forget that. And then they ask us, what is the weight of the plate of nachos? What is the normal force on the plate of nachos? What is the static frictional max force for the plate? What is mu static max? Okay, so let's start here by following the directions they give us. Down here they say draw the free body diagram and include components. So forces here, there is friction. Let's go ahead and get some forces though. So the first one I always like to get is gravity. I like to write the Fg over to the left, or away from where the triangle is going to be. That's kind of how I think of it. It's not always left. It could be right, I guess, if it was pointed the other way. All right, so Fg, but always straight down. Force normal, pointed 90 degrees to the surface. Right? What else? And I think just one more force, right? And that's it. And this is the resistive force that stops it from sliding. And that's force friction static. So we have, that's it. There's only 3 forces on this free body diagram, technically. All right, we're going to draw some components, but I want you to realize technically there's only 3 forces. It's going to look like 5 or something here in a second, but it's going to only be 3 in actuality. All right, so then right here, we'll go ahead and label the new directions for our tilted axis. Reason being that force gravity doesn't get along with the other 2 forces. So we can either divide the other 2 forces to make them look like up and left or up and right, because they're pointing at these weird angles, right? So I have to either accept the fact that we're going to use weird angles and make them the new normal, or I can change them. And I'd much rather just change force gravity than change 2 vectors, right? To change force normal and force friction static. So let's just change force gravity. and accept the fact that this is the new normal with positive y this way, negative y this way, positive x this way, and negative x this way. So we just took the axis system and just tilted it. That's all we did, right? We didn't change it that much, just tilted it. All right, so, but we notice now that forced gravity doesn't get along with this axis system, right? Forced gravity does something like this. So we need to make forced gravity get along with this new axis system. So we'll have a piece of it point this way and a piece of it point this way. And so that's what we're doing to get this to make sense, right? Because we can't make sense of this vector right here in yellow, but we can make sense of its components, that one and that one, because that first one was negative y and the second one's negative x, so I can make sense of those. That highlighter's coming through like a lot, really heavy there. So let's try and let's try and change that. All right, so coming over here, let's go ahead then and split forced gravity into components. And what should we color it? Let's go brown. All right, so forced gravity. So a piece of forced gravity will oppose normal. See that? I just draw opposite normal, and it's going to be equal and opposite, so that gives you an idea of how long it should be. But I always draw it about to where FG ends. FGY is actually smaller than FG. So anyways, another piece of it is head to tail and points this way, head to tail with FGY, and points this way and is FGX. We can then draw in the right angle that always separates FGY and FGX, and we can draw in the angle of 20 degrees. So that 20 degrees is going to be that 20 degrees right there. All right, so I'm going to add a little color here just so you can see what I'm saying. So this angle is the same as this angle. All right. And that's important to realize because that's going to be our theta, right? This is theta right here, just like this is theta right here. Same idea. Okay, so before we go any further, I guess let's check to see what they want us to do next, right? It says draw the free body diagram, include components. So with the components, this looks like 5 forces, but in effect, there's only 3, the green ones, but we like to think of it as being 4. So when I do this problem, here's the redraw, which I like to do sometimes. When I do this problem, here's the nachos. All right. I like to think of the 4 forces that are going to be fighting over this plate of nachos, and the forces, whoops, let me go back to the forces are sometimes components, right? So FGY wants to go that way, or wants to push or pull the nachos that way. FN wants to push or pull the nachos this way. This is making me think about those nacho fries. Saw a commercial for that with the guy from Stranger Things the other day. And I've never had a hankering for fries at Taco Bell, but they look pretty good. So if I'm ever there anytime soon, I'm definitely have to try those. Anyways, all right, so getting back to this. Force, friction, static is going to point this way. And finally, FG of X will point down the ramp. And this plate of nachos hasn't moved because these forces are in equilibrium. And so that's what we're going to end up seeing in this problem, that they balance each other out. And therefore, you just have these stationary plate of nachos that just begins to move. But this is how they fight, right? So meaning, I can't zoom for some reason, that we have a positive x force here, force friction static, fighting with a negative x force, Fg of x, and a positive y force, force normal, fighting with the negative y force of Fgy. And I just want to redraw it because over here in this step, it just looks kind of crazy. It looks like there's a ton of stuff going on. Fg of x isn't even attached to anything. It's floating around in the bottom of that triangle. So I'm going to use this triangle to solve, but I just want you to understand that when you try and make sense of it, think of it like this. And this is a more logical way to think about the problem. Whereas this is just kind of the math that's going to help me get through the problem and solve it. Okay. Be sure to label FGX, FGY, FG. We did that in our triangle. Also label the hip, op, and adjacent. So I'm just reading what they're asking us to do. So across from the red angle, the 90 is the hip. Across from theta, the green angle is the op. And next to the green angle is the adjacent. All right, so far so good. Let's go ahead and go to the next part. Label theta twice in your drawing. I think we did that, right? We have the green angle labeled twice, so we're good. And that's it. That's just getting us through the first page, kind of setting everything up. And now we'll go ahead and apply some of this logic with some calculations and to determine the mu between the plate of nachos and the table. Mu, I was talking about this the other day in class, and mu is this idea that there's a characteristic, there's a quality that we put a number to that describes the frictional force between two surfaces. So maybe your tires on your car and the road, right? There would be a mu for that. And if your tires, instead of interacting with the road, interact with snow, then there will be a mu between your tires and the snow. And so the mu is dependent upon it's a characteristic of the two surfaces that are interacting, that are trying to have a frictional force between them. We have this idea of a mu, a ratio of friction and normal force, right? You can see right here, it's a ratio of static max friction to normal force, and that is what mu is. So you can have different amounts of frictional force between, say, your tires and the road, but there's only one mu between that certain set of tires and that certain road. So it's a characteristic of two materials, and it's dependent upon those materials. So there's different mu's for all the different materials you can think of, and that's kind of like mind blowing to think about. But there's that many mu values, right? But they are constant for those materials. So you know, if you go get another set of tires that are exactly like the ones you own and drive down the same road, that mu is going to be exactly equal. That's what we're saying. So it's kind of a characteristic, a property of those two surfaces is the way to think of it. All right, so anyways, for the mass of the plate of nachos in kilograms, or solve for the mass. Okay, solve for the mass. All right, so the mass was 1,500 grams, but we want it in kilograms because that's what we're going to use in this problem. So to get it to kilograms, we should remember our ladder. The star was in the middle, and this is where grams are. And then we had deca, hecta, and then killa. So what we had to do was move, start at grams. This is like Monopoly. We're on this square. We're going to go 1 square, 2 squares, 3 squares. So if we rolled a 3 in Monopoly, we would go 1, 2, 3, and end at killa. So our decimal has to move 3 times to the left, and right, because that was 1, 2, 3, and see how we're moving to the left. Decimal is going to move to the left in a similar way, except the decimal doesn't land on numbers; it goes around numbers. So down here, our decimal, which is at the end because I don't see it anywhere, so that's how you know it's at the end, is going to go 1, 2, 3. And so we're saying 1.5 kilograms is our answer for the mass. I'm just going to go ahead and write equals m. I guess I could have wrote out the word mass. All right. Solve for the weight, or FG, of the plate of nachos. Now, normally weight we like to think of in pounds, but in physics we like to think of it in newtons. And our formula for weight, we don't like to say weight. Instead, we say FG. But weight is the same as FG. In physics, we like to use the formula FG is mg. So let me change this to an arrow, just because I want to kind of point that out. And this means force gravity is equal to, and two quantities we're going to multiply by each other. This is the mass, and this is the baby G, or the gravitational field on the planet, which is Earth, which is 9.81 meters per second, also known as meters per second squared. So to solve for the force gravity, we're just going to multiply the mass, which we just said was 1.5. Let's see, so little room here. Let's write it over here to the right. So we're saying FG is equal to 1.5 kg, kilograms, times 9.81 meters per second squared. So this is going to be a little under 15, right? Because 9.81 is about 10. 1.5 times 10 would be 15. Let's multiply by 9.81. Getting about 14.715 newtons. All right, and there's our force gravity, which is also our hypotenuse, 14.715 newtons. So the reason I'm writing it over here is because I want you to see that our op and our adjacent are going to be smaller than that, right? So the gravity, the hypotenuse, FG, is our largest force. I just want to point that out. Okay, let's go back to where we were. Solve for FGY. Cos, I think the angle was 20. I should really know that. I'm going to guess right now. I live on the edge. All right, adjacent is FGY, and hip is FG. Let's look at if that's true, if all that is right. So 20 was our angle. You can see it right here. 20 is in the triangle. FGY, which we want to solve for, right? We want to get both these components. FGY is an adjacent, and because it's next to theta, so we're starting there. Theta is the green angle, the 20 degrees. So, all right, so I think we're good. Let's go ahead and plug in some numbers. We do know FG is mg, but we already solved for mg. We said it was 14.715. So let's write that right here. For FG. We'll put FGY on top, and we'll put cos 20 on the side there, and then multiply both sides to get FGY alone. All right, so if that's the case, cancel, 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 cancel. Something like that. Now it's a job for our calculators. So 14.715 newtons times the cosine of 20. It's kind of hard for me to see for some reason. I'm going to use some parentheses just to kind of split that up. I don't know why There's so much, too much going on there. All right, so let's type it in. Make sure you're in degrees. Radians are for rotating objects. All right, and we get 13.83. Newtons. All right. So there's our answer right there, 13.83 newtons. Now, does it check out? Is it acceptable? Well, it's acceptable if this is FGY, if it's smaller than FG, right? Because we said the hypotenuse is the largest side. So is that smaller than FG? Yeah, FG was that 14.715, so it does check out. Doesn't look like we made any mistakes. But that's a good way to just self-correct your problems, right? Like if you can spot it before you turn in a test or an assignment, little stuff like that helps. All right, so let's go to the other side now. And this is going to be solving for FG of x. They even tell us that up next to number 9. But we should realize that now we go back and check our triangle. FG of x is an opposite. We'll use the hypotenuse again. Could we use FGY? Sure. You could probably do some tan if you wanted, but let's keep it, keep it the same way every time. That way it becomes habit and it's easier to remember. All right, so FG of x is the opposite. The hypotenuse is FG, which we said is the same as 14.715. I'm going to go ahead and just write it in, right? I think we're comfortable with that. If you're not, you can write FG and then write another step. We're going to multiply both sides by 14.715. I want to solve for FG. Notice I'm sending the units for the ride too. They get treated just like numbers. Cancel, 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 cancel. FGX then is equal to 14.715 newtons times sine of 20. Now the sine of 20, sine does terribly with small angles between 0 and 90. All right, so let's go ahead and give that a shot. 14.715 sine 20. All right, I'm getting about 5.03, so quite a bit smaller. Newtons. Does that check out? Well, yeah, it's smaller than 14.715, which is our hypotenuse, so that's good too. Okay, so now we got two numbers describing FGY and FGX. Now we're going to go ahead and use those numbers to solve for the force normal and the force friction static. So what we'll see is we're going to go ahead and write Newton's second law in the y direction and then the x direction. It doesn't matter which direction you start with. It's just arbitrary. I just pick one. So I'll say sum of the forces. I'm actually going to use some blue marker. I think it's kind of bothering my eyes a little bit just because there's so much of my writing already in black on the page that I need to differentiate from it a little bit. So let's say sigma fx is equal to max. So there's Newton's second law in the x direction. Sigma is the Greek letter S for sum. Let's sum our x forces. Well, what were our x forces? That's a good question. So if you don't remember, go back to your picture and look. Well, we can see them right here, clearly on the redraw. We can see that force friction static was a positive x force and force gravity x direction was a negative x force. And sometimes that gets forgotten by students, right? Because they'll see this one, but they'll forget this one down here. And so that's why I like the redraw step. It puts them right where they're acting. And it gets rid of FG because FG is replaced by the two dotted lines. Okay, so anyways, those are our 2x forces. Which one's positive? Force, friction, static. Which one's negative? FGX. All right, let's go ahead and jot those in. The positive one gets the positive sign. So I don't even write the sign, but it's there. And the negative one gets the negative sign. And, okay, and now we're left with the mass, what was the mass, 1.5? Yeah, easy one to remember. And now the acceleration, the plate of nachos just begins to move, but when they say just begins to move, it's still equilibrium, AX is still 0, because it's like we're taking a picture right before they move. So we have 0 multiplied by 1.5, which is just 0. Force, friction, static. This is a maximum too, but we don't have to write it down right now. We'll go ahead now and solve just with these descriptions here. So we'll just add FGX to both sides. And we end up getting force, whoops, let me write that over. Force, friction, static is equal to FGX. All right. So that's what I wanted you to do there. Now, keep in mind on the test here, you will have to show me this work. I know some of you, I have had previous years where kids just remember this. And they're like, ha, beat the system. No, I want to see the actual work. I want to see this. This is a skill in the orange box right here that lets you solve tougher problems where the bottom part in yellow isn't always true. So that's kind of what we're building towards here, right? We might not get to that this year, but someday if you want to go back and learn more physics or you take the class in college, oh, come on in, you would have to, or you could do that, right? You could sign up, you could learn more physics. And so we're trying to build healthy habits, build a solid foundation of doing the problems, not just get the right answer, right? The right answer is kind of arbitrary, right? We're more interested in learning skills. All right, so that's good. So we're at a good place right there. We can also put a number there too. So we know that force FGX is 5.03. So let's go ahead and set that equal to 5.03. I'm just going to rewrite it. I think that's kind of lazy. So I'm going to rewrite that. And yeah, so just one last substitution there, right? I subbed in this, let me see if I can get a lot of color here. Subbed in this 5.03 right there. And that allowed me to say that force, friction, static was the same. All right, let's do the same thing over here. This time we'll write Newton's second law, F equals ma, for the x direction, but don't forget your sigma. All right. Once again, I think last time I was describing the y direction, I was describing acceleration. I said it's 0, but I think I was describing the x direction. And in the y direction, the acceleration is 0 because the plate of nachos is not accelerating into the sky or through the table. In the x direction, the plate of nachos is not accelerating right or left. Oh boy, this has been a long day. I see what I did. Okay. All right. I need to go wake up a little bit or something here. And I caught my error. If you were watching the video, you're probably like, Mr. Rodriguez just did all that in the x direction and said he was working in the y direction. Okay, so all my work here is for number let me see here. So I'm saying that I did all the work for number 11. So this is really the work for number 11. Sorry about that. If you want to just draw an X through that and write that right there, you can. Or that won't even work. What can we, let's just do this. Let's write, let me get my red pen here. So I'm saying that this is the X direction. If that, yeah, we just need to correct that. All right, so I did everything for the X direction. Okay, let's move on to the Y direction. Sorry about this, guys. All right. So we're working in the Y direction now. Okay. All right, and we'll correct this up here to read Y. Just as long as we're on the same page. Oh, and I see, and I gotta correct this now. So this should, oh, this is a mess. What if, dang, what if I just take this, as long as we know, I'll just take a red pen and just do that. But these are in the wrong place. All right, this is the answer for 11, and I'm about to do the answer for 10. Okay, let's give this a try. The mass is obviously still 1.5, but like we just said, there's no acceleration in the Y direction. And the Y forces are Fn pointed in the positive Y direction, Fgy pointed in the negative Y. So let's go ahead, write those in. Okay. You can go ahead and multiply over on the right. That's obviously going to be 0. Add Fgy to both sides. Cancel. All right, and look what we've proved, right? Fn is Fgy, and now we can just bring this number down. 13.83 in for Fgy. And what we proved then is Fn is 13.83 newtons. Struggling there. Write that. Okay. All right. So we have one more piece of the puzzle here. Okay. So a little bit of a mistake there, a misstep, but that's okay. We caught it, and you get the idea. Fgy is 13.83. Solve for up here, and then use that to solve for normal force here. Fg of x is 5.03, solve for over here. Use that to say that force friction static is 5.03. Okay. Let's finish the problem up here. So mu static is equal to force friction static max divided by force normal. And notice the max is on both of those, and that's fine. Max is just where it starts to move, because the mu is smaller before it starts to move, which is kind of weird. But that's for static. Static is kind of weird. So that's why. Force friction static max is 5.03. Kind of don't have a ton of room here. I'm just going to use this room underneath. Divided by force normal, 13.83. Notice the units cancel away. Mu is unitless. Get our calculator. Mu is usually a number between 0 and 1. It can be larger than 1, but it's usually between 0 and 1. This is 0.36. Whoops. Let's try this again. It's technically 0.364, but we'll just go with 0.36. That's probably good enough. All right, and this is mu static max. And so we should at least have the static there. So I'll write the little s in, but I will also write maximum, or max. Okay, so finally, what does mu stand for? And we said it's a ratio of frictional force to normal force. It's characteristic for surfaces. I can write some of those definitions down. It's a, this is for 13. It is a ratio. So we're describing this mu, right? Which is, this is mu. Is a ratio of force friction to force normal. It is a number that describes the frictional force between two surfaces. You could say between two unique surfaces, maybe. Specific surfaces, maybe that's a better word than unique. Or word choice, I mean. You can also just say that mu is the coefficient of friction. Or coefficient is just a fancy word for number. All right, that's it. So hopefully this is making sense. Hopefully, you can try the next one tomorrow on your own, quiz review number 3, and see how you do. All right, everybody take care.